Welcome to the course 131B, Real Analysis. This course, how it will be run is we'll have a mixture of in-class lectures through Zoom, office hours, and then we'll have these short videos on various topics that I'll start adding during the first week and as the course goes on. This first mini lecture will be on just what this course is about, to give you an overview, try to connect the concepts, give you a little bit of sense of what we're going to do. And also I'll go over all the resources that I've made available for you for this class. So first, I'll switch, most of these lectures will be on a tablet, and I'll switch to that tablet now. Now switching to the sharing my screen. So what this course is about, this is Math 131. This is Math 131B, Real Analysis. I assume that you have all taken Math 131A, and what Math 131A is about single variable calculus. Single variable calculus. That is, X is in R. And in this class, what we're going to do is we're going to take all these concepts. We'll introduce some new concepts on the way, but the main idea is to focus on the concepts that we had in 131A, and we take them to higher dimensions and to even briefly to infinite dimensions. And why we do this is that many of the interesting applications are actually in higher dimensions. So just to give some examples, if we take data analysis, here one way of one big problem in data analysis is that we have possibly high dimensional data. These points represent the different data. And we want to understand, one of the goals of data analysis is to find structures in that data, find representations of that data that convey the information that is needed in the application. And one of these is clustering. In the clustering application, we want to group the terms into groups in a way that the different groups somehow capture features of the data, and usually there's a notion of a distance that plays a role. So we want these groups to have small distance to a given center. But to do this, some of the issues that come up and some of the reasons why you might need 131B as a tool to understand these is that this data is often high dimensional. It exists, it could be, say, a DNA or gene expression data. It could be word counts of Wikipedia articles. It could be a variety of different things that can be represented by an element of Rn, R capital N. And this is just as tuples of real numbers. That's one of the issues. So we're no longer working on a single variable, but you have to work with high dimensional things. And this is already something that you've developed in linear algebra 131A. Now, another issue that comes up in this data is, and this varies depending on the application, is you need a notion of a distance in your space. And this idea of a distance should measure how close how close data points are to each other. Now, another application that you might be familiar with and is related to data analysis is optimization. How it's related is that the domain of optimization often involves a data set that has this form, but usually the goal is a little bit different. You have some function that depends on the data, and you want to minimize this function. So this is a cost function that you want to minimize. And the goal is minimize f on some domain x inside omega. And one of the big issues here is that we'd like to apply the tools that we have from single variable. We would like to look at the gradient derivative of the function set equal to 0. We would like to apply numerical methods that are similar to Newton's method or gradient descent, in case you're familiar with those. But many basic issues come before even discussing what method is for this minimization. And some of these questions are, does a minimum exist? Or how you would tell whether a minimum exists. And specifically, for which omega will this work? Which domains omega? Which domains omega and which functions? F. There can be a lot of very weirdly behaving domains and very weirdly behaving functions. Of course, in practice, generally things are much nicer, but we want to be able to say, what do we mean by nice, and give a basic sense, some basic assumptions that we can say guarantee that a minimum exists, and then give another set of assumptions maybe that would help us to find the minimizer for these problems. So that's definitely a place where we need a language to describe when a minimization is possible. Now, a third context that some of you may be familiar, this is something from 134 and 135, systems of differential equations and different ODEs. So in ODEs, we are looking at, and also related concepts like partial differential equations, we are looking at solving equations of functions, namely the derivative of f is equal to some other function of f and t, and we have some initial data and t given by some value. We want to solve this equation. Now this is an equation, but it's not an equation in x, it's an equation in the function. And this idea of viewing this as an equation of where the unknown quantity or unknown variable is a function instead of a variable x a function, specifically a function of time, usually a function of time. It could be a function of x as well, depending on what variable you want to use, but the unknown quantity is the full function with all of its function values that we're looking for. And in this case, it turns out that similar methods and ideas from real analysis actually allow to prove that such equations have solutions. But what this leads to is the need to talk about f being an element of the space of functions, of a space of functions. And this space is very big. if we just say a space of functions, it is any function that you could write out. It's not just high dimensional, it's infinite dimensional. And the word infinite here just comes from the fact that if you, these will generally be vector spaces in the sense of 115a, but they will have infinitely many linearly independent functions. Specifically, an example would be that if we have the interval 0, 1, and if we have the functions f0 is equal to 1, f1 is equal to x to the 1, f2 is equal to x squared, and fn is equal to x to the n, these are linearly independent. I won't prove this now, but it's believable. If you take combinations of these, the only way to get 0 is if you take the trivial combination. So because there are infinitely many x to the n's, the dimension is infinity. So all of these concepts, they require, we want to still talk about the same things. We want to solve equations. We want to minimize functions. We want to have a notion of when we are close, when we are far away, and how to group data according to distance. But to do that, we need to introduce new concepts. We need to introduce new concepts. And to study their properties. And to study, one of the core concepts that will be a unifying thing throughout this class is that of a distance, on a distance and of a metric space. So x being some kind of set of objects. So it's crucial concepts. First, an x is a set of objects that could be different things depending on applications. We'll see many examples in other lectures. And a distance function. dxy. It takes into points in x, so x and y in x, and outputs a number, something that is number r that's between 0 and infinity. We don't allow the number to be infinite. In some applications, you might allow that. We don't. And this distance of function can be very general. Most of the time, we'll give an explicit formula for it. But what we will assume is generally 3 properties, and we'll discuss these a lot more later, but I want to say them now, is that it turns out that this distance, there are only 3 important properties for a distance that we will need. Properties. One is positivity. So for every pair of points, the distance is a non-negative real number. Two is symmetry. That for every pair of points in your space, distance x, y is equal to distance y to x. And 3 is reflexivity. That if the distance is 0, first of all, distance x to x is equal to 0. And in general, if you have 2 points, then distance x to y being equal to 0 is equivalent to x being equal to y. So this is the core concept, and all these other concepts that we will need to, such as continuity, etc., they will be defined in terms of these notions. So, and the reason that we do this is that a more general language allows us to see similarities between these different problems. So on the one hand, optimizations, on the one hand, ODEs, lots of other applications as well. We want to find a common language to describe all of these settings. And the crucial notion indeed is a distance, and from it we build metric spaces. This is one of the crucial concepts of this class. And this allows us to define many of the things that we are familiar with. We are able to define convergence and distance. We can define things like open and closed sets. We can define things that we have used a lot in your classes, closure, boundary, etc., that describe the geometry of sets in various ways. So we are able to already talk about some geometric ideas. We can define things like bounded sets. And then two of the things that are difficult to extend, so thinking of single variable real calculus, convergence and distance, these are all come pretty straightforward from the distance function, as we will see, but there are some other things that we will need that are basic things in single variable calculus, but we need to extend them. One is, what does it mean to be continuous? And other concepts pertaining to continuous functions, the most important ones for optimization is extreme value theorem. And another one is intermediate value theorem. But the unfortunate thing, or the other way of thinking, is the interesting aspect of this class is that whereas in single variable, it's quite easy to state the conditions of intermediate value and extreme value theorem, in higher dimensions and in general metric spaces, we need to be more careful about the assumptions. And for extreme value theorem, we will actually need a new concept called compactness. And for intermediate value, we will need a new concept called connectivity. These concepts are more complicated in higher dimensions because the sets that you can have are much more complicated than in single variable case. To wit, this idea is that in a single variable case, sets are generally just intervals of points. They can be a little bit more complex than that, but generally the assumptions concern in intervals of points. But even in the plane, the sets can be significantly more complicated. They can include cusps. They can wiggle in various ways. Maybe they don't include all of their boundary, etc. So in higher dimensions, we have more complicated sets, and therefore we need a language to describe these more complicated sets. And this is generally the outline of the first half, roughly half of the class. Now, as applications, once we've developed this language, we will go into things that are specifically of interesting applications. One concerns series of functions. It's very similar to series of numbers, except that we have variables inside the summation. So Taylor series and Fourier series. And these are now series with a variable, and we have to talk about the convergence of them. We want to talk about how do these converge. It turns out that there are different ways that these can converge. There's a whole language and issue that surrounds when can we talk about these infinite sums of things, and when do they give correct formulas for them. Fourier series, of course, is a very important application in practice. You see it in data analysis all the time. And I want to spend a lot more time on Fourier series than I do on Taylor series because of that those applications. Now, and the final thing that comes up in a lot of other classes, specifically optimization, is, and also differential equations, is higher dimensional differentiation. Here, the issue is that we have functions that are defined on a subset of Rn, and in the worst case, they have values in Rm, and both of these are not equal to 0. Now, what does it mean for f to be differentiable? Well, on the first hand, what does it mean for f to be continuous? And then on the other hand, f to be differentiable. So these are some of the core concepts and roughly the order at which we will go through them. The differentiability is the last week or so of classes. Series of functions will be before that about 2-3 weeks. And the metric space concepts is what we will discuss up to that point. That will develop a lot of the terminology and conceptual knowledge that we will need to do that. So what I want to do next is show you some of the resources that we have for this class that I've prepared for you. So to do that, I'll share my screen for a little bit. So all of our meetings, of course, will be on Zoom, but we have, in addition to that, we have a CampusWire website that you should all be a member of. If you haven't, then you should join it. There is a link on the CCLE that will allow you to do that. A few things about the features on this site and why I chose it. So there's a class feed. You can post things on it, choosing a category. I would suggest choosing, say, homework or one of these weak categories so that we stay organized about which topic you are about. If you have questions about logistics, the virus, exams, etc., use those categories. You can write a title, you can write a note, you can add pictures, you can add links, you can link files, you can use LaTeX to write formulas. I think that's one of the nice features of this program. Now, if you have a post, I've made a couple here. You can like other people's posts. So now I like my own post. You can add comments to that at the bottom of the page. In those comments, you can add little GIFs, you can add links, you can add formulas in LaTeX or Markdown format. You can add emojis if you so choose. So lots of, that way you can interact here. One thing I think this is great for is that if you're stuck on a homework problem, you can post here a question on that homework problem, and then there can be a discussion connected to that. And also, if you're stuck, you can first see what was asked before. So this is a better way than to emailing me a question, because I like that everybody can see this discussion that goes on, and that way you can also help each other on the questions. Now, another feature that I would like to highlight is direct messages. You can send direct messages to me, and those you can use if you have a specific question about anything. You can use them as a substitute for emails. At this point, if you want, I do recommend you can send me a little introduction about yourself. So just a small text or a short one-minute video telling me a little bit about yourself and why you're taking this class, about your background, what you struggle with, what you're excited about, etc. This gives me a more personal connection of who you are, and that's one of the ways you can use this direct messaging at this point. And any questions about anything, you can send them as DMs to me. You can also send to each other direct messages and to the TA. And now, another feature on CampusWire that I think is pretty cool is that we have these chat rooms. So chat rooms allow you to participate in discussion about various topics. So I made already some of these, anticipating that some things that we might want to share. One of them is about technology and resources for online learning. So already I've posted here about how to set up a UCLA VPN if you haven't done so. And there's also the link to the textbook that are available. So all of these textbooks you can access them by a Springer link. The only one that you cannot access through that is Rudin's Principle of Reanalysis, but which I do recommend as a resource, but it's not strictly speaking necessary. And another resource that I mentioned here is related to how to submit your homework as a single PDF. And I mentioned some of the apps that you can use for that. Now, other discussions here that I have started, one is on homework. Here you can discuss, have a chat room format for discussion about homework problems. You can discuss about lectures. This is also a great place where you could ask questions for following that you would like me to discuss in following lectures, or that you found confusing. I might then try to address that with a mini video or in the chat or some other way. So use these to communicate what you find confusing or what you would like to be more explained. And finally, a great thing here, I think, a great potential here is that you can form study groups through this website. So I formed 2 tabs here. One, the chat rooms. One is for looking for study groups. You can post here if you want to find somebody else to work with. And another one is if you already have a study group, you can look for members there. So a good way you could do this is you could post saying, okay, I want to study together. These are my available times. Feel free to direct message me. And once you have a few people, a critical mass, say if you have friends, you might start from there. Then you could post that, hey, we have a group going on. We're meeting Wednesdays at this time. If you'd like to join, please do. The more you have to talk about with good chemistry, I think that's generally good. I would recommend around 4 or 5 people for a group. You could also work in pairs, etc. Of course, all has to be done virtually this time. Should not be meeting in person. So that's our CampusWire website. Another resource that we have is CCLE. I will mostly use CampusWire, but CCLE is important for some things. So I will use it for announcements that you can find on the front page. So currently you should review all of these announcements that I've posted in the past week or so. And then I will post resources for the different weeks. So one of these resources will generally include the homework. The first week we do not have homework. They will include the Gradoscope assignment environment where you can submit your homework. And they will include notes, possibly videos, and other content that you may find useful. So the first thing that it will be there always for every week is a sheet covering the topics of that current week. Because online learning can be difficult, I recommend you should structure your week. And I want to help that with giving you the reading that you should do. The reading will always include 3 parts. There will be a reading from Rudin, a reading from Pew, and a reading from our official course textbook, which is by Terence Tao. The Tao is more expository. It doesn't include very many proofs. I would recommend focusing on Pew. And Pew is available on Springer Link. If you have access to Rudin, that's also a great thing to look at. It's much more hardcore. You might struggle reading it. A great thing about Pew also is that he has lots of pictures and videos. I at least found it very appealing looking at the concepts from his book. Now, big thing in this class is definitions. Each week we will cover different definitions that are related to different theorems. The first week we will talk about metric spaces, open and closed balls, etc. So these are definitions that you should make sure that by the end of the week you definitely know these concepts. For each of them you should know a couple of the crucial examples. You should know some of the main properties that they enjoy. Now, related to these concepts, there are theorems and there are sort of open-ended questions that you should be able to answer. You should be able to tell when a set is open, closed, etc. What does it mean to converge? How do you prove that something is converged? So some of these are very open-ended, depending on the topic, but these are about skills and concepts that you should try to learn from the reading, from the vet lectures, etc. Now, there are some minor supplementary topics that I will add videos on during the week that you should review. And then there is a summary of the videos and lectures that will be provided, as well as the mini lectures that I will make. So these are concepts that I will have a short video on and cover. So this will give you a guide. This will be a weekly guide on what the course that week will be about. And you should refer to that. This is also the place where all the exams will appear. There will be a midterm tab here when the time is right. There will be a final tab here, etc. And all the grade exams will be processed through Gradoscope, where you all should have been added already by now. This is a place where you can upload the answers. This is probably what your other classes will be using. And we will also use as well. These are some of the main resources that are available, and you should look on these websites. Also look through the syllabus of the course. It's on CCLE, it's also on my website. It discusses a lot of these policies, the resources that are available. It discusses the exams, and maybe the one thing I want to mention in this video still is the percentages for the class. So we have the midterm, we have a very homework-based class because of the circumstances. So 50% comes from the homework, which is about 10 homeworks. We have 2 midterms, 15% each, and we have a final, which is 20% each. The homework you can collaborate on. The exams are take home. You can use all resources, but you have to do them alone. Additionally, there is an extra credit opportunity. So to encourage you to use the CampusWare website, I will give a little bit of extra credit depending on how much you use it individually and how much you contribute to that. And then there will be another opportunity. This will be expanded during the first, towards at least maybe the first few weeks of the classes, towards the mid of the course, is that there will be an extra credit opportunity to write something about a topic that is not covered in this class, but is closely related. There are a number of topics that are very interesting for other classes, and by writing a short paper that is, I think, around 3 to 5 pages, including main definitions, main theorems, at least 1 or 2 proofs, this is a great way that you can deepen your knowledge in this class, and this is also an extra credit opportunity. So review this syllabus. You also see a weekly schedule on it, and that's that. Yeah. So that was all for now. I will upload during the next few days more of these videos for the first week, but this was the first try. Maybe they will get a little smoother over time. So look forward to seeing you on Monday. Until then, Monday. Yeah, until then, bye for now.